And today our kinematics section is going to focus on vertical motion rather than horizontal. Okay, we learned those 4 kinematics equations for horizontal, right? V equals V sub O plus AT. We got all 4 of those? Yes? Okay. And we did okay with our homework with the horizontal motion. Simple enough? Okay. Today we're going to move into vertical. So these problems become just a little bit more complex. This is where we start drawing our origin. This is where we start determining if things are positive or negative based on a vertical coordinate system. Okay, so we're going to get started today with free fall. So we're talking about free fall on the surface of the Earth. We're not looking at it in an elevator. We're not looking at it in a vacuum. We have the acceleration due to gravity acting on all these falling objects. Okay, so acceleration due to gravity is still considered constant acceleration, which means that we can use those kinematics equations we were given. Okay, this free-falling constant acceleration will be due to the acceleration due to gravity. All right, and we're going to talk about that a little bit more extensively here in a second. Okay, so what do you think? Do you think heavier objects fall faster than lighter objects? Yes or no? How many of you think no? How many of you think yes? Anybody yes? Do you remember who discovered that?
Newton.
Galileo. Okay. Galileo. So, objects with different masses fall at the same rate. Okay. We don't consider their mass at all when we're looking at velocity, acceleration of objects that are in motion. Okay. In fact, we don't look at their mass even when we're doing horizontal motion, right? We didn't have mass in any of those equations. It didn't have anything to do with how much it weighs. Once we start looking at momentum, that will have something to do with its mass, but for right now it doesn't. Okay? So the answer is no. Heavier objects do not fall faster than lighter objects. And we're going to watch yeah, it's going down, right? We consider down to be in the negative direction. It's gravity's always pulling things back toward the Earth, okay, which is the center. Okay, that's where gravity stems from. So everything with that acceleration due to gravity, or little g, is going to be negative 9.8 meters per second squared. Okay, we said it was due to acceleration due to gravity. It's constant. We've talked about that. We're going to use all those same kinematics equations that we have prior, okay? V equals V sub O plus AT, but we're going to make 2 little substitutions. Now, instead of having an A for our acceleration, we could substitute that with a little g. Okay, those are both forms of acceleration. Regular A and regular little g are both accelerations. And then what's the other switch do you think that we could make if we're dealing with vertical motion? Yeah, Mitch, what do you think?
Replace X with Y.
Very good. Replace X with Y. Okay, since we're dealing with vertical motion instead of horizontal, we're going to use Y sub 0 for initial position instead of X sub 0, just like we'll use Y instead of X for final positions. Very good. Okay, so I'm going to give you a second if you would like to rewrite those 4 kinematics equations either in your notes or on your note card with these replacements made. I'll give you a chance to do that. If you can just simply recognize when we're doing vertical things that these are the variables you should use, that's fine. You don't have to rewrite them, but if you're more comfortable distinguishing horizontal and vertical equations, you are more than welcome to do that. So I'm going to give you just a couple minutes now to get that done if you'd like. Okay, so suppose that a ball is dropped from a tower 70 meters high. How far will it have fallen after 1 second, 2 seconds, and 3 seconds? So you will need your calculator out and in use today. So I'm going to start this by drawing a diagram of what this motion looks like. Okay, here's our tower, and here's my origin right here. That's where my motion starts from. That's where I choose things to be 0, 0. Okay, my initial position is 0. My time is 0, all starting at that spot at the top of the tower. You don't have to write the little zeros, but this plus sign tells me where you're choosing your origin at. Okay, you could choose your origin to be at the bottom of the tower. That's just going to make a little difference in the numbers that we use, okay, in most problems. And then what is this length right here? Or height, I should say. 70 meters, okay? Let's take a look again at what the question is asking us. The question is asking us, how far will it have fallen? Which means we're solving for which variable? Distance, or y in this case because it's vertical. So does the 70 meters really make a difference to us? No, especially since we chose the top of the tower to be our origin. Okay, the 70 meters makes no difference to us right now. All right, so let's talk about what else we do know. We're going to go ahead and start with seeing how far it's fallen after 1 second, which means our time would be equal to 1. What else can we start to pull out? What things do we always know, Peyton?
Y original is 0.
Yep, good. Y sub 0 is 0. What else? G, good. G is negative 9.8. Oops. And we know one other thing from the word dropped. Yeah?
V sub 0 is also 0.
Very good. V sub 0 is 0, right? If it's thrown, then it might have some initial velocity, but since it's dropped, it has no initial velocity. So we're missing a final velocity variable, which means that narrows down what equation we can use. We can use, I think, that second equation, right? Y equals y sub 0, v sub ot plus 1/2 gt squared. Okay, we're solving for y, so we're not using that 70 meters here at all. All right, so does everyone agree with what I have here? Why did our displacement come out negative? We're ending up below where we started. So we're basically acting as though this is our coordinate system right here. Okay, that's where I wrote my little origin up here. We're ending up about 4 meters below where we started, 4.9 meters below where we started from. Okay, so that's why our y is negative. You go ahead and plug in that second 2 times. Solve for 2 seconds and solve for 3 seconds, and we'll see if we agree. We've solved all 3 of those time intervals, and that's telling us that at 1 second we've fallen about 5 meters, okay, 4.9. 2 seconds we've fallen about 20 meters, or 19.6, and by the time we've gotten 3 seconds we're down at 44.1 meters. Okay, so those intervals between the 1 and the 2 seconds and between 2 and 3 seconds should be increasing, right? They shouldn't be evenly spaced apart, otherwise we'd be looking at no acceleration. Since we've got acceleration, we've got to notice that those intervals are getting farther and farther apart. It's moving a farther distance during that 1 second time interval as it continues to fall. Okay, does that make sense? All right, good. All right, let's look at this kind of same situation here, but instead of dropping the ball, that means we're going to throw it downward with an initial velocity of 3 meters per second. So we still have our diagram here. We still pick our origin at the top. Nothing really looks different here, except it has an initial velocity instead of a 0 initial velocity. So what's the numeric value, or what's the magnitude of our initial velocity? 3 meters per second, but one more.
Negative.
Very good. It has to be negative 3 meters per second. And why is that negative important?
Because it's being thrown down.
Yes, because it's going down. All right, so in these vertical problems, we've got to really pay attention to whether we're throwing a ball up, whether we're throwing it down, whether it's being dropped, all those types of things, because that makes a difference in how long these things take, how far they go, things like that. Okay? The time we're given is 2 seconds. G doesn't change. We're solving for our final position here. So we can use the same equation that we used in the past, right? Y equals y sub 0. All right, what'd you get, Carl?
Got negative 25.6.
25.6 meters. Okay, so it has fallen below where we started, 25.6 meters. Do we all agree with that number? Okay, so is that larger or smaller, okay, or has it fallen farther or not than when it was just originally dropped at the 2 second time interval? It's gone farther, right? And does that make sense conceptually that if we put some speed on it at the beginning, if we throw it, it should have traveled a farther distance in that same time interval, right? Because it has some initial velocity at the beginning. Does that make sense? All right. So this one says if a person throws the ball upward into the air with an initial velocity, we want to calculate how high it goes and how long the ball is in the air until it reaches their hand again.
Would it be a positive?
Yep. Michael asked if the initial velocity would be positive. That is correct because we're throwing it in the upwards direction, which we consider to be the positive direction. Okay, the diagram here is just showing that basically the purple's on the way up, the green's on the way down. Okay, it's going straight up and coming straight back down. We're not dealing with what are called projectiles yet. Projectiles are things that are moving both horizontally and vertically. We're not to that point yet. We're just looking at things that are going straight up and coming straight back down. Okay? So all we're told here is that we have an initial velocity of 15 meters per second. But we can pick a lot of other things out because some things just don't change. Okay, one of those things is G. What's one of our other things that doesn't change?
Position.
Initial position, good. Okay, what do you think?
Final position would be 0 also.
Final position. We're going to look at this in 2 segments. Okay, because our first question is to answer how high it goes. Okay, that means we're only looking at the purple section of this particular diagram. We're going to see how high it goes basically until it reaches this first part. So we're looking at just this half right here. So when something reaches its peak height, right, when I throw an object in the air and it reaches its peak height, what happens to its velocity? It's 0, right? It stops for that little millisecond. So for the first half of its motion, it's got an initial velocity of 15 meters per second and a final velocity of 0 because on its way up, halfway or reaching its peak height, it reaches that 0 velocity. So we can also pick out here that v is equal to 0. Okay, our final velocity is equal to 0. All right, because we're looking at how high it goes, which means we're looking at its peak height. We're looking only for that first half of the motion. Okay, which means we're going to solve for y. We're missing one variable here which constitutes, or it dictates which equation we can use. We're missing time, so that means we need to use equation 3, which is v squared. Okay, do we all agree with that equation? Are you doing okay picking out equations by yourself? Okay. Should our displacement here come out positive or negative? Positive, right? Because it's going up. We're going to end up above where we started. Our peak height should be above where we started.
Wow, that's great.
These are made up. They throw it really high? Yeah. All right, tell me how high. Like what, 30 something? Or?
192.
Oh, 109. That seems a little high.
Yeah, I
got
think
11.4.
11.4. All right. That would be pretty strong arm. So here we're looking at only half the motion, or we're looking at up and back down? Up and back down. So there's a couple different ways you can go about solving for this. I'm going to show you what I think is the easiest. You could realistically use any of the equations, but I think it's easiest to look at the 1/2 of the motion and then multiply your time by 2. Okay, because it's going to take the same amount of time to go up as it does to come down. So I think it's easiest to use our very simple equation, V equals V sub O plus GT, to solve for time for the first half of the motion, okay, which would be only this purple segment, or this segment right here again, okay, only the first half from here to the peak height. Once we solve for time, though, it's essential that you multiply that by 2, okay? I'll see a lot of people forget to do that. If you're solving for time and you only go to peak height, which means your final velocity would be 0, you've got to be sure to multiply that by 2. So here at peak height, our final velocity would be 0. Our initial velocity would be 15. We know g is negative 9.8. And we're going to solve for time. All right, and our time comes out to something like 1.5 or 1.4 or something. 1 point what? 1.53. So a lot of you will get into the habit of stopping there. Okay, but it's important that you realize, since we chose final velocity to equal 0, that's got to be only to peak height. It's only reaching its crest right now. We've still got to have the time accounted for on the way down, so we just multiply that by 2. Okay? Something to remember, velocity and acceleration are not always in the same direction. Okay, consider the problem that we just did. We threw a ball into the air with a velocity of positive 15 meters per second, yet our acceleration was gravity, which is negative. Okay, so velocity and acceleration do not always have to be in the same direction. Okay, they don't always have to have the same sign. Okay, you have got to know that at an object's highest point, its velocity is 0. Okay, that's got to be something that's ingrained in your brain for these physics problems, is that when an object reaches its peak height, okay, it's gone as high as it can go, it's going to stop for just that little second. So its object's velocity at peak height is 0. Okay, that's something we're going to use very, very, very often. Okay, even when an object's at peak height, what's the acceleration at that point? Negative 9.8 meters per second squared. Okay, still has gravity acting on it, still has acceleration, but might have a 0 velocity. So that's that one exceptional case we talked about a little bit earlier with our acceleration problems. Okay, so this is that same problem we just did. We found out how long it takes to reach maximum height. We looked at how long it takes to reach maximum height. That was the first time that we solved for, right? 1.53. We multiplied it by 2 to reach time up and time down. But we're going to look at velocity on the ball when it returns to the thrower's hand. So we want to find final velocity. Could you do that without doing any math? Yes. Okay? What goes up must come down. Okay? And it's going to come down with the same speed that it left our hand at. Okay? So I threw it upwards with 15 meters per second velocity. It's going to land in my hand with 15 meters per second velocity. Okay? So we can do that one without having to think. Okay, it's gonna land at the same speed that it left. Okay, those are for things that are thrown, not things that are dropped, obviously. Okay. At what time does the ball pass the point 8 meters above the person's hand? This one we do have to do some math for. Okay, so we determined with our first problem that it's going to travel upwards of 11 meters, right? A little bit over 11 meters. Yet we're going to look at what time it's going to pass a point 8 meters above the origin. Okay, so we think that at 8 meters, we're going to find out what time it hits that. Okay, so let's think about what we know again. We know that y is equal to 8. We know y sub 0 is equal to 0. We know v sub 0 is equal to 15. Do we know the final velocity at 8 meters? No, we didn't solve for that. What we're solving for here is time. So we have an equation that we can use, since we don't have final velocity, to solve for time, right? Okay, we know this is 8 meters because it's 8 meters above where we started. Can anyone see the problem that we're going to run into yet? T and t squared. That doesn't work. So what do we have to do to solve that? We got to use the quadratic formula. We have to use quadratic formula because we are left with here negative 4.9 t squared plus 15t minus 8 equals 0. So there's our quadratic formula components, negative 4.9, positive 15, and negative 8. So for our quadratic formula here, why are we getting 2 times? How do we know? Okay, first of all, did you get 2 positive numbers out? What if you would have got a negative number out?
You know it's wrong.
Yeah, we know it's wrong. Why?
Because time is negative.
I mean, we can't have negative time. Okay, so that doesn't work. So if you ever get a negative out, you know it's got to be the other one. So why are we getting 2 positive possible answers?
Is it going up?
Yes, perfect. It's going to hit 8 meters on the way up, and it's going to hit 8 meters on the way down. Okay, so both of those answers are correct. It hits 8 meters on the way up and on the way down. So we've got to have 2 different times there. All right? Okay, and we will get really, really, really good at graphing next week. But we're going to start introducing position versus time graphs and velocity versus time graphs. We've talked just briefly about position versus time graphs already, yes? Okay, tell me what the slope of a position versus time graph, what's that give us? Velocity, very good. That gives us velocity, remember, because delta x over delta t is our very, very first equation for velocity. So slope of the line tells us velocity, very good. And for all linear things here, we're going to use the equation y equals mx plus b. Okay, so you don't need to know the same equation as, I'm not talking about that right now, but for these linear ones, we use y equals mx plus b. And to find the slope, we use the equation rise over run, okay, or delta y over delta x. Do we all know how to solve for the slope of a line, hopefully? That's not something that I got to spend time on? Okay. Okay. So now let's look at a velocity versus time graph. We spent a couple minutes on this just briefly describing what the motion looked like, but now we're going to be able to really interpret and solve some things from a velocity versus time graph. Okay, do we remember what the slope of a velocity versus time graph tells us? Acceleration, very good. Okay, the slope of a velocity versus time graph tells us acceleration. And we talked through this particular graph looking at basically when it speeds up, when it sets its cruise control, things like that. Do you remember that? Hopefully, yes. Okay, good. Same equation as blah, blah, blah. Okay, anytime it's linear, we're using y equals mx plus b, and we're solving with rise over run for our slope. Okay? You can do one other thing with a velocity versus time graph. Okay? In a velocity versus time graph, you can solve displacement, right? And displacement is how far you ended up from where you started, or what basically what distance or displacement is covered during a certain time interval. You can find that from a velocity versus time graph by finding the area under the graph. Okay, so area under the graph in a velocity versus time graph will tell you displacement. Okay, you've got to be careful here about using the axes. Okay, when I say under the graph, I mean from the line to the axes, and then you stop, right? Hopefully I'll show you an example of that problem here in a second. But thank you, Michael. Okay, so we're going to look at this next graph, and we're going to find the displacement from 5 to 8 seconds. Okay, we're going to look at our next graph, and we're going to find displacement from 5 to 8 seconds. So just keep that in mind, and I'll bring the graph up here. Okay, we are going to find displacement from 5 to 8 seconds. 5 seconds runs here to here. 8 seconds runs here to here. Okay, so all we do is find the area of that box, and that'll tell us the displacement during that time interval. Okay, so what would the length of this side be here? 3 seconds. And the length of this side here? 40 meters per second. So if I'm going to multiply those, I'm going to take 40 meters per second times 3 seconds. I'm getting rid of seconds, and that's leaving me with 120 meters. Okay, so that's how much distance, or that's our displacement during that time. So you can find two different major components from a velocity versus time graph. You can find an acceleration during a time interval, and you can find how much displacement was covered, or how much distance was covered during a particular time interval. Does that make sense? Okay. Let's think about this one last thing right here. If I asked you to find the displacement from 0 to 5 seconds, what do I do? From 0 to 5 seconds. Yeah, very good. I have to break it up. Okay, so I have one triangle there, a rectangle here, a triangle there. Okay, so you've got to break it up into manageable pieces. Okay, same thing if I asked you to find the displacement of the entire system, you'd be solving it, you'd be using this, okay, breaking it up into different portions that work best for you. And you can break it up lots of different ways, but you should be able to add them all together. Okay, does that make sense? Okay. So I'm going to put your homework up on the board.